Hi, and welcome to this demonstration of the Problem Solution Space Co-Evolution Support tool developed by the University of Hildesheim for Work Package 5. The purpose of this tool is to support the co-evolution between different types of artifacts in terms of detecting unintended divergences between them. For example, the variability model as part of the problem space may introduce configuration options which can be configured by the end user, but are not used in build or code artifacts as part of the solution space, which leads to no effects no matter how the user configures them. Another example is the usage of configuration options in build or code artifacts which are not defined in the variability model and hence can never be configured such that the related functionalities are never part of a valid product. In order to detect such divergences, the tool first identifies relations between problem and solution space artifacts by checking which configuration options are used in which build and code artifacts, and which build or code artifacts reference which configuration options. Based on this mapping between problem and solution space artifacts, the second step identifies divergences between them by analyzing the mapping for any incomplete or inconsistent entries. The result of this analysis is input to the third step, which tries to correct the detected divergences. The ultimate goal is to apply corrections automatically, but at this point the tool only provides proposals for corrections to the developer. The actual tool is developed as a set of kernel Haven plugins. Kernel Haven considers variability information in code, build, and variability model artifacts. The architecture therefore consists of 3 extraction pipelines. For each pipeline, specific extractors can be used to extract relevant information from the respective type of artifact. In this case, we use the Undertaker code extractor, the kbuild-miner build extractor, and the kconfig variability model extractor, which create the necessary internal data models on which our co-evolution support plugins operate. As introduced before, the Problem Solution Space Mapper plugin realizes the first step of creating the mapping between problem and solution space artifacts. This mapping is passed to the divergence detector, which identifies possible divergences and sends its results to the divergence corrector for proposing corrections. Realizing the 3 steps as individual plugins enables different variants of the shown setup, such that other tools may use only the mapping or the detected divergences, but not the corrections, for example. The respective setup of kernel Haven is defined in a configuration file, which the pipeline configurator reads at startup to configure kernel Haven before its actual execution. In the remainder of this video, we'll use this configuration file to show the different steps one by one. However, first we start with downloading and installing kernel Haven, as well as the plugins for the Problem Solution Space co-evolution support. Then we create the Problem Solution Space mapping, identify possible divergences, and have a look at the proposed corrections for a small and artificial example we developed for this video. Let's start with the hands-on demonstration of our tool. First, we need to download kernel Haven and the required plugins realizing the Problem Solution Space co-evolution support. Therefore, we navigate to the kernel Haven GitHub website. There we choose the main infrastructure repository. The other repositories host the individual plugins. Then we download the entire kernel Haven release, including all plugins. The release is an archive file which we have to extract to our favorite location. We prepared a separate directory for this purpose, to which we extract the main infrastructure, all plugins, a set of predefined directories, for example for caching intermediate data or the final output of a plugin, and a set of predefined properties files which define certain kernel Haven instances. However, for the Problem Solution Space co-evolution support, we need specific setups which we defined in advance for this video. We copy these properties into the kernel Haven directory and open the first setup, which defines the sole execution of the Problem Solution Space mapper. Each properties file contains a set of individual configuration options, which are described in detail in the properties template of kernel Haven. Here we focus on those options relevant for the Problem Solution Space co-evolution support. These are the source directory, which contains our example for applying our tool to. Next, for the code model parameters, we defined the Undertaker extractor as our code extractor by its fully qualified main class name. In the same way, we defined the kbuild-miner extractor for the extraction of variability information in build artifacts, and the kconfig reader extractor for extracting variability information from the variability model. The most interesting part is the definition of the actual analysis. This is our Problem Solution Space mapping plugin, which creates the mapping between our different artifacts. Further, we need to define how that plugin should identify configuration options, for example in code and build artifacts. This is done by a simple regular expression, which defines a variable starting with the prefix config_ as a configuration option. With that configuration file, we can start kernel Haven via the command line. We navigate to the directory where we installed kernel Haven and start the main infrastructure as a Java jar archive and pass the properties file we investigated as a parameter. Depending on the host, the creation of the mapping takes some seconds to complete. After that, we find an Excel sheet in the output directory, which we defined in the properties file. The columns hold information like the name of variables identified as configuration options, their state in terms of whether they are used in build or code artifacts or are only used or defined in the variability model, and the code files as well as specific code elements controlled by the variables as defined in build and code artifacts. For example, the variable config calculation defined in the variability model is used to control the code element starting from line 42 in main.c, while the variable config doBuildModule is undefined, meaning that it is not defined in the variability model, but controls the presence of the entire file main.c as defined in build artifacts. On this basis, the divergence detector identifies unintended divergences between the different artifacts. Therefore, we need to slightly adapt the properties file by adding the new plugin as a subsequent analysis step in kernel Haven. This is done by concatenating the plugin calls, such that the divergence detector uses the result of the mapper plugin as an input. We start kernel Haven again with this extended setup, which again takes some seconds to produce the results. In the output directory, we find a new Excel file, which now contains the detected divergences as well as the produced mapping as in the previous Excel sheet. Each divergence type points to a specific divergence and has symptoms in both the problem and the solution space. For each divergence, we try to provide enough information to understand the detected problem, like the missing definition of a configuration option, while it constrains the presence of certain code elements. Finally, this information is again input to create corrections of such divergences, which requires another adaptation of the kernel Haven setup. Here we add the divergence corrector plugin as part of the concatenation of analysis plugins. Now, the divergence corrector consumes the results of the divergence detector, which in turn uses the results of the mapper plugin. This extended setup is used to start kernel Haven again, which produces the third result in our video, providing proposals for correction of the previously identified divergences. In the resulting Excel sheet, the first three columns from the left are the same as for the identified divergences, while the fourth column contains corrections for them. Currently, these are only textual descriptions of possible actions a developer may perform. In summary, we showed you the current state of our problem solution space co-evolution support. More information can be found in the previous deliverables and on the GitHub websites. Thanks for watching this video.